We're tackling the problem longest increasing subsequence, which we want to try and solve with minimum complexities of on squared time and on memory. Given an array of integers, we need to find the length of the longest subsequence where the elements are in strictly increasing order. To give an example, here are some of the LeetCode test cases. As you can see in example 1, our longest strictly increasing subsequence goes from 2 to 3 to 7 to 101 within this array. So our length is 4. In example 2, we've got 0 to 1 to 2 to 3, so from index 0 to index 1 to index 4 to index 5. The length of that increasing subsequence is 4. Finally, we just have an array comprised of 7s. Our longest strictly increasing subsequence is 1. So, let's take a look at the possible methods we can use to solve this problem. We have A, dp plus memoization, B, prefix max array, C, greedy, or D, 2 pointers. I'm going to pause for a couple of seconds while you think about your choice. So, for those of you who were able to get this, congratulations! And for those of you who just want to see the code, the answer here is A, dp plus memoization. Our application does have a brute force approach, but I'm not going to go into it in too much detail here. As you can see, it would be a lot better to go into our optimized solution. So let's take a look. So, generally speaking, we use dp with memoization to optimize the calculation of the length of the longest increasing subsequence. In this given solution, we start with our memory array, that is, we maintain the array memory to store the lengths of the subsequences for each sequence of the input array nums, starting from our 0 index all the way up to whatever the max is, which in this case, according to the constraints of the problem, is 2500. After we've got our memory array set up, we start with the base case where memory I equals 1 for all indices, since a subsequence with a single element has a length of 1. So, for example, in example 3 here, we'd probably be finishing with every single one of these having that length of 1. Now, going back to our solution, we iterate over the array nums from left to right, and for each element, we iterate from the beginning of nums up to the current index, and including the current index. If we find an element that is smaller than the current element, we update the length of the subsequence at the current index using the maximum of the current length and the length of the subsequence ending at the previous element plus 1. So we're performing all of these calculations here, and I'll explain how in the line by line. Eventually we'll be returning the maximum length stored in memory, which is given by this variable. Essentially this ret, by the way, I'll talk about it a little bit now. It's just a reference that stores the result for the current index within our memory array. So, let's go through this line by line so I can make this a bit more explicit. And we'll start with this length of lis function. So this takes in the input array nums as our parameter, and as you can see, we assign nums underscore to the nums vector that we're keeping globally here. We insert int min at the beginning of nums to handle the edge case where nums is empty. After that, within C++, we're using memset, and this initializes our memory array with -1 to indicate that no values have been calculated yet. and we'll be making use of this -1 within our LIS, or longest increasing subsequence function. Speaking of which, after we've used memset, we're calling the LIS function with LIS 0. So that's the starting index 0, and after we've called it, we're going to subtract 1 from the result, whatever that result may be, since we've inserted this int min in the beginning, artificially adding an extra element we don't need. Oh, well, we need it for our calculation, but we certainly don't need it when we're returning our result. So let's take a look at how the LIS function works. At the most basic level, it's a helper function. It's taking in this index as a parameter, and it's returning the length of the longest increasing subsequence starting from that index. Inside the function, the first thing we're checking is if the index, the current index, is beyond the size of our nums array. If it is, we return 0, since there are no more elements to consider. After that, we create the reference ret, which stores the result for the current index in our memory array. So I mentioned it a little bit earlier. If the result is not already calculated, i.e. not equal to -1, we directly return this ret reference. After that, we initialize ret to 0, which represents the length of the current subsequence starting from the current index. We then iterate over our nums array as mentioned, and we start from the current index using next equals index, and we go all the way up to the end of the nums array like so, iterating this variable next each time. And then we perform the crucial check. Inside this loop, we're checking if the element at the current index, that's nums index, is smaller than the element at the next index, as you can see here, nums next. If it is, it means that we can extend the subsequence. So we recursively call LIS with the next index to get the length of the subsequence starting from next. And actually we're maximizing among these values. After that, one thing we must do is increment ret by 1 so that we're including the current element in the subsequence when we return ret. And that's pretty much it. That's how our LIS function works. What it will do is simply return the length of the longest increasing subsequence for the index we're currently at, making multiple recursive calls if necessary. So, a very, maybe not the most intuitive if you're new to dynamic programming, but quite a basic one if you're not. If you need help with understanding how dynamic programming works, I would recommend this as a good entry point. Dr. Ibrahim goes through multiple, maybe 25 dynamic programming problems in total during the course of this course, and it has quite a steep learning curve, but it really is worth it if you go through it all. Anyway, for the purpose of our application, we are done with this video. We'll look one more time at the very brief problem statement and possible solutions. You should be able to recognize that to solve longest increasing subsequence, we can use dynamic programming with memoization to solve it. There is an explanation given here, and I do know there are probably some better versions of this code. However, we've included this code for you in C++, Python, and Java. You'll note that generally speaking, the Python and Java solutions make less use of the global variables, which is a bit of a no-no, but it's the way that I'm using them in C++ at the moment. In any case, that's it for this problem. We'll be continuing in the course with the longest common subsequence problem.